Welcome to Sleepy Science Facts. It's wonderful to have you here, nestled in your cozy space, ready to unwind and discover some gentle insights about the world around us. Feel free to relax and settle in as we drift softly into the soothing realm of crystals and their fascinating forms. If you enjoy these calm explorations, a quiet like and subscription would be very comforting for us both, allowing this peaceful journey to continue together. Crystals form delicate patterns that come from a very precise arrangement of atoms or molecules. At the heart of each crystal structure lies a lattice, a carefully ordered pattern that determines how it will grow as time unfolds. Each lattice is unique, shaped by the specific chemical composition of the material and the gentle forces that hold the particles together. As a crystal begins to form, tiny particles line up in this repeating fashion, creating a strong foundation. This orderly arrangement helps every crystal maintain its distinct external shape, reflecting the harmony of its inner structure. The way these particles bond governs how the crystal expands, influencing its dimensions and the overall beauty of its form. The symmetry and consistency of these arrangements contribute to the splendid variety seen in nature. Each type of crystal emerges with its own special character, defined by these foundational patterns. Moving forward, we can delve deeper into how these intricate details unfold, revealing even more of their serene nature. The response of crystalline materials to magnetic fields reveals a fascinating aspect of their internal structure. This responsiveness, known as magnetic susceptibility, reflects the arrangement of atomic magnetic moments within the crystal. These moments are the tiny magnetic fields created by the spins of atoms. Each crystalline material holds its own character, retaining its unique susceptibility as an intrinsic property. When placed in a magnetic field, the alignment of these moments can change, but this transformation generally remains stable. External factors, like prolonged exposure to strong magnetic fields or fluctuations in temperature, might gently influence the alignment of magnetic domains. These slight shifts occur in an orderly manner, but do not alter the fundamental magnetic characteristics of the crystal itself. Over time, the core essence of the material stays intact, preserving its identity. The harmony within the crystal structure governs how it interacts with magnetic forces, reflecting a balance that is both remarkable and soothing. Continuing deeper into this subject allows us to appreciate the subtleties within the world of crystals, where each property flows into another with calm precision. The process of species evolving unfolds gently across vast periods, shaped by the shifting tapestry of the environment. This evolution can be seen as a series of subtle adaptations as life forms respond to gradual changes around them. Over millions of years, these small adjustments accumulate, leading to a rich diversity of species. Each organism, in its own quiet way, reflects the influences of its surroundings. As environments transform, some life forms thrive, while others may fade away. This phenomenon, known as natural selection, allows certain traits to become more prominent within populations, enhancing survival in changing conditions. In this serene cycle, the origins of new species emerge from the remnants of those that came before, illustrating the delicate balance of existence. Within this slow dance of change, life's complexity blooms, with each species intertwining in a web of connections. The flow of organisms adapting and evolving creates a dynamic landscape of life. Continuing to explore this intricate journey not only reveals the wonders of nature, but also invites a deeper appreciation for the profound rhythms of evolution. Minerals nestled within crystals possess a remarkable quality, allowing them to engage with the surrounding environment over the years. This interaction unfolds gradually as external chemicals seep into the structure of the crystal, initiating a slow transformation. Over centuries, these gentle reactions caress the mineral composition, creating a subtle dance of change that reshapes the original crystal. As time passes, the crystals metamorphose, their inner workings drawing upon the elements nearby. This process can eventually lead to the formation of completely new types of rock, each carrying the history of its environment within its layers. The transformation reflects not only the passage of time, but also the delicate balance of nature's cycles. In this quiet evolution, the beauty of minerals captures the essence of change, revealing how life on Earth is intertwined with both permanence and transience. Each new formation tells a story of interactions, constantly evolving within the tranquil embrace of its surroundings. Such slow alterations open the door to hidden wonders, just waiting to be discovered. Each crystal boasts a unique melting point, a defining characteristic that marks the transition from solid to liquid. This temperature is not merely a number, it represents a fundamental limit, a threshold that indicates when the orderly arrangement of atoms within the crystal begins to break apart. As the temperature rises, the internal structure, the very essence of what gives the crystal its clarity and form, starts to change. Gradually, the orderly pattern that has held the crystal together for so long loses its grip. Atoms that once danced tightly in harmony begin to drift apart, surrendering to the heat. The melting point signifies a moment of transformation, where the solid state yields to liquid, flowing freely without the rigid structure it once possessed. This seamless transition highlights the relationship between temperature and the physical properties of materials. Crystals, with their defined melting points, illustrate the delicate balance of forces at play. Each unique melting point further reveals the diversity of crystals, whispering secrets of their atomic makeup and the environments from which they originated, inviting us to ponder the wonders of the natural world. Zircon crystals are remarkable in their ability to endure the passage of time. Their strong crystal lattice contributes to their impressive durability, allowing them to withstand immense geological forces and the challenges of weathering. This lattice is formed by a tightly bonded arrangement of atoms, creating a stable structure that resists alteration, even when faced with the transformative power of nature over billions of years. As these crystals form in the depths of the earth, they encapsulate the conditions of their surroundings, preserving the history of the rocks they inhabit. Their resilience protects them from the effects of erosion and chemical changes, enabling them to remain intact through cycles of metamorphism and tectonic activity. This tenacity is why zircon crystals become valuable records of ancient times, offering glimpses into the geological past. The interplay of time, pressure, and heat has little effect on their structural integrity, allowing them to tell stories of the Earth's history with remarkable clarity. Their endurance invites us to quietly reflect on the slow, inexorable changes that shape our planet. Internal stresses within a crystal are a fascinating aspect of their long-term behavior. As geological movements occur over eons, these stresses can gradually accumulate, influencing the crystal's structure. Very slowly, the applied forces may lead to the development of microscopic cracks. These cracks are not stark or sudden, rather they appear gently over time, like the quiet unfolding of a story. As these tiny fissures form, they begin to spread, creating new internal surfaces that alter the crystal's arrangement. This process is slow and subtle, reflecting the nuanced dynamics of the Earth's crust. The overall integrity of the crystal becomes gradually weakened as these intricate changes take place within. Yet, this transformation is part of the natural cycle of the crystal's life, emphasizing its connection to the ever-changing landscape of geological processes. Each tiny crack tells a story of resilience and adaptation, reminding us that even the strongest structures are subject to the gentle forces of nature. In this delicate balance, the enduring nature of crystals continues to engage in their own quiet journey, always in harmony with the world around them. Crystals possess the remarkable ability to grow larger over time, a process that occurs at a serene and measured pace. As they exist within their surroundings, they quietly attract and attach new atoms or molecules. This interaction is not rushed. Rather, it happens gradually, like whispers in a soft breeze. Each atom finds its place among the existing structure, conforming to the orderly arrangement that defines the crystal. This gentle accretion builds the crystal's form, layer by layer, contributing to its eventual size and beauty. The changes are subtle and often imperceptible day by day, yet over long periods, they lead to a more intricate and expansive structure. As the crystal continues this slow dance of growth, it remains embedded in the Earth's embrace, quietly responding to its environment. The harmony of this process reflects the delicate balance within nature, where everything evolves without haste. Each moment adds depth to the crystal's journey, inviting a sense of calm and continuity, ready to explore the endless possibilities that lie ahead. Within the delicate architecture of crystals, there exist imperfections known as dislocations. These are subtle line defects that create slight disturbances in the orderly arrangement of atoms. They form pockets of strain energy, where the regularity is momentarily disrupted. It is in these tiny irregularities that fascinating processes unfold. Over time, these dislocations have the ability to move and rearrange themselves, responding slowly to the internal and external forces acting upon the crystal. This movement is gradual, almost serene, as the defects weave through the crystal's structure. As they shift, they influence the overall properties of the crystal. Changes in strength, flexibility, and other characteristics emerge from the interplay of these line defects. The flow of energy within the crystal is altered ever so gently, creating a dynamic balance between order and disorder. This quiet interaction highlights the complexity of the crystal's internal world, where every small motion contributes to its larger nature. As the dislocations drift, they remind us of the constant, subtle transformations occurring in all matter, providing a gentle rhythm that is always ready to embrace what comes next. In the quiet journey of crystallization, a transformative process unfolds as materials transition from a disordered state to a structured crystalline form. This transformation is accompanied by the release of latent heat, a gentle outpouring of energy stored within the material. As atoms come together, finding their precise positions in the crystal lattice, they relinquish this internal energy, allowing the structure to grow more stable and enduring. This release of heat is a fundamental aspect of the thermodynamic nature of crystals. The energy freed during crystallization creates an environment where the newly formed structure can thrive. As the temperature shifts, the material balances itself, retaining its integrity in response to the changes around it. The delicate dance between order and energy continues within as the crystal patiently adapts to its surroundings. The ongoing interplay of latent heat and structural stability underscores the profound intricacies involved in crystallization, evoking a soft sense of continuity within the realm of material existence, inviting further exploration into the calm depths of this natural process. Each crystal holds within it a specific heat capacity, a clear measure of the energy required to gently raise its temperature. This value remains stable under typical conditions, allowing the crystal to maintain its serene state. Even as warmth envelops it, the internal structure remains largely unchanged, resilient and steadfast against everyday fluctuations. Over long spans of time, however, there exists the potential for slow, subtle changes. If exposed to intense radiation, the crystalline framework may experience cumulative atomic displacements. These gradual shifts can slowly alter the properties of the crystal, yet such transformations are rare and occur over vast periods, hardly disturbing the harmony of its existence. In the quietude of the crystalline life, this stability brings comfort. It reflects the enduring nature of the material, remaining unyielding to transient influences. As time moves gently onward, the crystal perseveres, embodying a peaceful rhythm amidst the slightest whispers of change. The realm of crystals thus remains an inviting space, ripe for further gentle exploration. Diamonds, as a unique form of crystalline carbon, showcase remarkable stability. This stability arises from the strong covalent bonds that intertwine the carbon atoms, creating a robust structure capable of withstanding extreme heat and pressure. During the long journeys of geological time, these bonds resist disruption, allowing diamonds to maintain their integrity deep within the earth. Encoded within the very essence of diamonds is a history that reaches back to ancient parts of the Earth's mantle. Here, amidst layers of rock and pressure, the formation occurs slowly, a quiet process that unfolds over countless years. The conditions in which diamonds develop cast a sense of timelessness, as if they embody the endurance of the planet itself. Though often associated with glamour, the true beauty of diamonds lies in their quiet resilience and stability. Their existence reflects a deep connection to the Earth's history, a silent witness to the intricate processes of nature. While they remain concealed beneath the surface, they carry with them echoes of a distant past, waiting patiently for the next phase of their journey. The world of diamonds invites contemplation, gently urging thoughts toward the mysteries of nature's persistent forms. Crystals, with their orderly structures, can hold within them trapped ions or molecules. These trapped entities find a resting place within the crystal lattice, creating a delicate balance of forces. The presence of these ions or molecules generates internal electrostatic forces that interact softly with the surrounding crystal framework. Over time, these interactions can influence the crystal's electrical properties in subtle ways, gently altering its behavior without any sudden shifts. As the days and nights pass, the internal dynamics of the crystal harmonize with these trapped components, allowing for a gradual evolution in its characteristics. This quiet process reflects the deep connection between the crystal and the elements that reside within. Different conditions like temperature and pressure can affect how these trapped entities behave, influencing the stability of the structure. Over prolonged periods, the slow changes within the crystal emphasize the patience of nature itself. The internal world of a crystal remains a serene realm, filled with intricate interactions that unfold continuously, illustrating a hidden yet stable lifestyle. Each crystal stands as a testament to the gentle flow of time, ready to share its secrets with those who pause to observe. The tensile strength of a crystalline material describes its resistance to being pulled apart, a property that holds deep significance in its structural integrity. This strength remains a stable characteristic, defining the limits of how much force the crystal can endure before it gives way. Beneath the surface, microscopic cracks may begin to emerge slowly over time. These tiny imperfections, often forming in response to external stress, can propagate subtly, creating a slow dance of change within the material. However, despite these gradual developments, the bulk strength of the crystal typically remains intact, serving as a testament to its resilient nature. This stability offers a sense of reassurance as the internal structure continues to uphold itself against the test of time. Even as cracks form, they rarely disrupt the crystalline order entirely, maintaining the overall integrity of the material. In this way, the long-term behavior of crystals showcases a continuous balance, where strength and vulnerability coexist, a quiet reminder of resilience enveloped within the gentle embrace of nature. The inner life of these materials flows steadily, a peaceful existence filled with soft transformations that resonate through time. The motion of surrounding fluids, such as water or air, can gently influence the surfaces of crystals over extensive periods. This action is a slow but steady process, where the constant flow of these fluids can gradually erode the surfaces of the crystal. With each passing moment, the edges begin to smooth, and the fine details are subtly altered, creating a soft transformation in appearance. This delicate erosion unfolds quietly, slowly wearing away sharp edges while enhancing the overall roundness of a crystal's form. Intricate patterns that once defined the exterior may become less defined, washed away softly by the passage of time. As these fluids move and dance around the crystals, they carry minute particles and deposits that gently abrade the surface with an almost tender touch, reshaping the crystals as they coexist in their environment. In this harmonious interaction, the crystals adapt, evolving their surfaces through this long-term relationship with the surrounding elements. The result is a tranquil reminder of nature's gentle forces at work, a continuous cycle of change that unfolds with an ever so gentle rhythm. Each particle and ripple contributes to a serene passage of time, where the essence of the crystals remains undisturbed, yet forever changed, existing in a state of soft transformation. Ice crystals nestled within the vast expanses of glaciers have the remarkable ability to remain stable for thousands of years, existing in a serene frozen state as long as temperatures stay below freezing. Within these ice crystals, the hydrogen bonds connecting the water molecules form a rigid structure, creating a solid framework that can withstand the test of time. This structure is not merely a collection of molecules, it is a symphony of stability, holding the ice in a delicate balance, resisting the pull of warmth that would set it free. Melting requires a significant amount of energy, a gentle awakening that disrupts the tranquil order of the ice. Only with the application of consistent heat can those bonds begin to break, allowing the crystals to transform into liquid. The frozen beauty of glaciers, standing silently through millennia, speaks to the resilience of these ice structures, embodying a stillness that persists amidst changing environmental conditions. Each crystal holds stories of the time it has endured, encapsulating within it the history of the atmosphere and the earth. Even in the gentle warmth of the sun, the glaciers remain steadfast, an intricate interplay of form and function, quietly waiting for the right moment when change will finally come. Within the serene confines of a crystal lattice, subtle internal vibrations, known as phonons, weave through the structure in a constant, gentle rhythm. These vibrations are not merely background noise, they embody the thermal energy present within the material, a quiet dance of movement intrinsic to the very nature of the crystal itself. Each phonon represents a tiny quiver, an echo of energy that flows seamlessly throughout the lattice, connecting all parts of the crystal in harmonious unity. As these vibrations travel, they help to maintain balance within the crystal, creating a dynamic environment that is both stable and alive. The lattice, composed of highly organized atoms or molecules, supports these movements, allowing thermal energy to propagate without interruption. This internal communication contributes to the overall integrity of the material, ensuring that it remains resilient over time. In this way, even the stillness of a crystal holds complexity, as the phonons continue their soft, persistent motions, quietly influencing the state of the crystal. Each phonon, a testament to the energy contained within, reflects the interplay of motion and stillness, embodying both stability and flow in a timeless cycle. Through this delicate balance, the essence of the crystal remains, waiting patiently to reveal its secrets in the quiet of the universe. In the vast expanse of space, large asteroids and comets traverse their own ancient paths, occasionally crossing the Earth's orbit. While these events are infrequent, their impacts can introduce profound changes to the planet's environment, rippling through the delicate fabric of ecosystems. Over timescales that stretch across tens to hundreds of millions of years, these celestial encounters can reshape landscapes, alter climates, and influence the trajectory of evolution itself. Upon impact, the energy released can create significant disturbances, sending shock waves through the atmosphere and altering temperatures. Dust and debris may fill the air, blocking sunlight for extended periods and transforming habitats. The aftermath of such events often sets the stage for new opportunities and challenges, pushing life to adapt and evolve in unexpected ways. Over eons, these impacts become markers in time, each contributing a layer to the Earth's geological and biological history. They remind us of the intricate interplay between celestial mechanics and life on Earth, inviting contemplation of the slow march of time and the ever-changing nature of existence. Here, in the quiet patience of the universe, the cycle of transformation continues, with each event becoming part of the tapestry of life that unfolds ever so gently. Through the ages, the Earth's continents have experienced cycles of coming together and drifting apart, creating what are known as supercontinents. This grand process unfolds over hundreds of millions of years, driven by the slow movement of tectonic plates beneath the Earth's surface. As these land masses coalesce, their assembly profoundly influences the planet's features and environments. The formation of a supercontinent can reshape ocean currents, directing the flow of water in new patterns. These currents play a crucial role in distributing heat and nutrients throughout the oceans, affecting marine ecosystems and the climate. As the land masses unite, they also alter atmospheric circulation, creating new weather patterns that can promote or inhibit specific forms of life. Eventually, these great supercontinents break apart, leading to a new distribution of land and sea. This process fosters varied habitats, enhancing global biodiversity. Different species adapt to these changing landscapes, evolving in response to the shifting environments that emerge. Each cycle contributes to the Earth's dynamic history, a continual movement that transforms the planet over unimaginable timescales, weaving a complex narrative of life and change across eons. The gentle rhythm of these cycles continues to shape the world, an ongoing dance of land and sea that invites quiet reflection on the nature of time itself. In the quiet remnants of ancient seas, salt crystals, known as halite, slowly take form and endure. Over vast stretches of time, the gradual evaporation of seawater leads to the concentration of minerals, allowing these crystals to emerge and cluster together. Once formed, these halite crystals can persist for eons, hiding beneath layers of sediment and waiting quietly in the Earth's embrace. The strength of the ionic bonds connecting the sodium and chloride ions within each crystal contributes to their resilience. These bonds hold the structure tightly, allowing the salt to remain stable as long as it remains dry and undisturbed, protecting it from the whims of weather and time. Beneath the surface, these expansive salt deposits can stretch endlessly, a silent testament to the geological processes that shaped them. When water is introduced, the delicate balance shifts. This addition can dissolve the halite, breaking apart the crystalline structure with ease, returning the crystal to its ionic state. If conditions permit, the water can then evaporate once more, nurturing the potential for new crystallization. The cycle continues, a gentle rhythm of dissolution and reformation, illustrating the enduring relationship between salt and water, carried through the ages. Each grain of salt holds the stories of its past, waiting patiently as time flows onward, ready to share its secrets once again. Within the delicate lattice of a crystal, the bonds between atoms or molecules weave a tale of strength and stability. Each bond represents a powerful attraction, tightly holding the crystal together, ensuring its integrity across the ages. This interconnected network forms a solid foundation, allowing the structure to withstand the passage of time without easily breaking or shifting. The nature of these chemical bonds creates a balanced internal condition, where each component works in harmony with the others. The stability means that a crystal can remain unchanged in form, even when surrounded by the forces of nature that would otherwise erode softer materials. The resilience of the structure is a reminder of the enduring power of atomic forces, quietly working in the background. Even as eons drift by, these bonds remain steadfast, offering a sense of permanence amidst the changes of the world outside. In this calm stability, a crystal stands, bearing witness to the slow, gentle flow of geological time. As dust settles and landscapes shift, the bond remains, quietly preserving the essence of its existence, ready to engage with the world around it when conditions allow. This silent strength allows the crystal to carry on, waiting in peace, embodying a gentle continuity that invites exploration and contemplation. Within the heart of certain crystals lies a fascinating property known as piezoelectricity. When these crystals experience mechanical stress, such as compression or stretching, they respond by generating a small electric charge. This transformation is a subtle dance of the internal arrangement of atoms, shifting in reaction to the forces applied to them. The regularity of their structure allows this generation of energy to occur in a calm, predictable manner. The change happens at a microscopic level, nearly imperceptible to the senses, yet powerful in its implications. The electric charge produced is a gentle expression of movement, a reflection of the internal dynamics responding to external pressures. This phenomenon underscores how the internal properties of crystals can intertwine with physical actions in their environment, revealing a quiet interplay between structure and energy. As stress is applied and the charge forms, the crystal continues to maintain its integrity, showing resilience even in response to external forces. This continuous cycle of stability and response fosters a sense of enduring strength, illustrating the remarkable nature of these crystalline forms. The stillness surrounding the crystal stands in contrast to the energy it can produce, embodying a serene balance that persists through time. The exploration of such properties within crystals invites a deeper appreciation of their silent yet dynamic existence, waiting patiently for the gentle touch of change that may stir their hidden energies. The bulk modulus of a crystal serves as a measure of its resistance to compression, revealing a fundamental characteristic of its structure. This property reflects how much a crystal can withstand being squeezed before it changes shape. It is intricately linked to the interatomic forces that hold the atoms together within the crystal lattice. These forces create a delicate balance, ensuring that, even when pressure is applied, the crystal can maintain its form. The lattice structure, arranged in an orderly manner, plays a vital role in this stability. Each atom is positioned in relation to its neighbors, forming a cohesive network that contributes to the overall stiffness of the crystal. Under typical environmental conditions, such as changes in temperature or minor fluctuations in pressure, the internal arrangement remains robust, allowing the crystal to endure stress and return to its original state. As the bulk modulus indicates, this enduring property symbolizes the strength of the interatomic bonds, which can adapt while retaining an inherent rigidity. The stability offered by these bonds is a testament to the crystalline form, allowing it to act steadily in the face of external forces. This calm resilience highlights the quiet beauty of crystals, nurturing an appreciation for their structural integrity and the gentle dynamics at play within. With each subtle shift in their arrangement, they reveal a grounded harmony, poised and ready for the next whisper of change that may come their way. Certain crystals, such as diamond and silicon carbide, exhibit remarkable hardness, enabling them to endure harsh conditions that would challenge many other materials. This exceptional strength arises from the strong covalent bonds formed between their atoms. In these crystals, each atom shares electrons with its neighbors, creating a robust network that contributes to their overall durability. The arrangement of these atoms within a rigid lattice structure further enhances their resilience. Each atom is precisely positioned in relation to others, forming a pattern that supports the crystal's integrity. This orderly organization is key to understanding why these materials can withstand both pressure and temperature changes without undergoing significant deformation. Under stress, the strong covalent bonds and tightly knit lattice work together, allowing these crystals to absorb energy without fracturing. The bond strength remains stable over time, ensuring that even under extreme conditions, they retain their hardness and shape. This stability speaks to the fundamental properties that define these exceptional materials, nurturing a sense of calm from their unyielding nature. In their steady existence, one can find a serene reminder of order and strength amidst the complexities of the natural world. The carbon cycle is a gentle, ongoing process that orchestrates the movement of carbon through various components of the Earth, including the atmosphere, oceans, land, and living organisms. This intricate dance unfolds over vast geological timescales, connecting the different spheres of the planet in a quiet rhythm. In this cycle, slow processes play significant roles in regulating the levels of carbon dioxide in the atmosphere. For instance, rock weathering gradually breaks down minerals, releasing carbon into soil and water. This carbon may eventually find its way into rivers and oceans, where it can be absorbed by marine organisms. Conversely, volcanic outgassing brings carbon back into the atmosphere, releasing it after extended periods stored within the Earth. Over millions of years, these processes maintain a delicate balance, ensuring that carbon levels remain stable enough to support life. The seamless exchange of carbon among the land, oceans, and air highlights the interconnectedness of natural systems. With each cycle, the tranquil passage of carbon shapes the environment, quietly nurturing the world as it continues its timeless journey. The movements of tectonic plates create a gentle yet persistent pressure within the Earth's crust. As these plates grind against each other, the slow friction can cause stress to build in nearby crystal formations. Over long periods, this pressure leads to tiny fractures, slowly breaking the crystals apart. Each small crack contributes to a gradual process of disintegration. Initially, the crystals may still maintain some integrity, but as this continual grinding continues, the stress accumulates. Larger formations start to crumble into smaller pieces, each fragment holding traces of the original structure. These small pieces scatter, resting in the earth, waiting silently as they become part of a larger cycle of change. Over millions of years, this slow transformation contributes to the richness of the geological landscape. The once majestic crystal formations find new life in varied forms, gently reminding us of the enduring nature of change. This quiet, ongoing process weaves a story of resilience and continuity, inviting calm reflection on the movements deep within the earth. Beneath the surface, plant roots engage in a quiet struggle with the stones of the earth. As they grow, they extend their reach outward and downward, seeking nutrients and moisture. This slow, steady pressure gradually interacts with rocks that hold crystals within their depths. Over many years, the roots apply gentle force, pushing against the surfaces where the crystals reside. As this pressure continues, it begins to create tiny fractures, slowly working to break apart the crystalline structures. The roots, in their pursuit of sustenance, can open pathways that were once sealed. Each small movement contributes to the gradual transformation of the landscape, allowing the crystals to yield to the persistent embrace of nature. Over time, the once solid formations can become fragmented, their delicate pieces scattered and softened. This interaction illustrates yet another way that the natural world reshapes itself, revealing the slow dance of growth and change that occurs beneath our feet. The process carries on, intertwining with the passages of time, inviting a sense of peace in the understanding of life's quiet resilience. Within the delicate arrangement of a pure crystal, a unique property emerges: electrical resistivity. This characteristic gently defines how a crystal interacts with electric currents, indicating the extent to which it opposes their flow. The structured lattice of atoms, aligned in a precise order, provides a stable foundation for this trait. As currents move through the crystal, the inherent resistivity remains largely unchanged, offering a dependable measurement over time. While external factors such as temperature fluctuations and imperfections may cause temporary variations, the core resistivity remains a reliable constant. The ordered nature of the crystal's internal structure acts like a quiet guardian, preserving its fundamental qualities against the influences of its surroundings. This stability allows for a gentle understanding of how energy can flow or be hindered as it navigates through such an organized system. Each crystalline formation subtly reinforces its own identity, inviting a sense of harmony in its continuous interaction with the world around it. The quiet persistence of these properties speaks to the beauty of nature's order, a serene reminder of the small wonders that exist within the fabric of reality. The rare mineral known as hollandite possesses a fascinating internal structure, characterized by its unique arrangement of barium and titanium. Within this composition, channels are formed, creating open pathways through the crystal. These channels, while integral to the structure, also serve an important role in the behavior of the crystal itself. As various atoms or ions find their way into these spaces, the properties of hollandite can shift. The presence of different particles can lead to variations in conductivity, stability, or even the formation of new structures within the existing framework. This flexibility within the rigid crystal lattice reflects a delicate interplay between order and adaptability. By allowing other elements to occupy its channels, hollandite subtly transforms, showcasing a dynamic balance within its solid form. Such an arrangement contributes to the ongoing story of the crystal, as it remains poised and ready to change, yet still anchored in its distinctive characteristics. Each unique formation within the crystal serves as a quiet testament to the complexity hidden in nature's design, revealing a world of possibilities in the molecules that exist just beneath the surface. Talc, recognized as one of the softest minerals, reveals a tranquil beauty in its crystalline structure. This structure is composed of layered arrangements of atoms that stack neatly upon one another. Each layer consists of magnesium, silicone, and oxygen, creating a harmonious balance that is both delicate and stable. The layers are kept together by weak van der Waals forces, which are gentle attractions between the atoms. These forces allow the layers to slide past one another with ease, contributing to talc's softness and smooth texture. Despite this gentle nature, the overall integrity of the crystal remains intact, allowing it to endure over extensive periods. Found nestled within metamorphic rocks that may be millions of years old, talc embodies a sense of history and stability. The very layers that allow softness also speak to resilience, existing through time while preserving their unique structure. Over the ages, these crystals have quietly witnessed the slow unfolding of geological processes, each layer a memory of its journey. In this ongoing presence, talc remains a gentle reminder of nature's ability to balance strength and fragility. A crystal's journey in a solvent is governed by the concept of solubility. Each type of crystal has its unique characteristics, determining how much of it can gracefully dissolve in a liquid. This interaction unfolds delicately as molecules of the solvent come into contact with the crystal, gently breaking apart its structure and surrounding the solute. With time, as more and more solute enters the liquid, a point is reached where the crystal can no longer dissolve. This moment signifies the saturation point. At this stage, the solution has embraced as much of the solute as it can, and any additional crystal will simply settle at the bottom, retaining its form. The balance between the solvent and the solute remains in a state of quiet equilibrium. As the solution sits, the undissolved crystal remains a soft presence, while the dissolved particles mingle with the liquid, creating a harmonious blend. The saturation point marks the limit of solubility, a gentle reminder of the delicate dance between matter and its surroundings. This balance continues quietly in nature, inviting contemplation in its simplicity, ready to flow seamlessly into the next moment. Within certain crystalline materials, the presence of radioactive elements reveals a subtle yet profound aspect of nature. These elements undergo a process known as radioactive decay, where unstable atomic nuclei transform into more stable forms over extended periods. This decay occurs at a slow and steady pace, following predictable half-lives that are intrinsic to each element. The half-life of an element describes the time it takes for half of its radioactive atoms to decay. As this process unfolds, energy is gradually released, but at a rate that feels gentle and unhurried. Over geological timescales, this slow decay contributes to the internal energy dynamics of the crystalline structure, defining how it influences its surroundings. This enduring stability is a fundamental characteristic of such materials, allowing them to persist in nature for millions, even billions of years. The quiet rhythm of decay continues, marking the flow of time within the crystal's framework, leading toward a state of balance. The slow transformation within the crystal offers a peaceful reminder of the natural processes that unfold in the world, an unceasing journey that is both calm and enduring, ready to gently carry on. In the heart of every crystal lies a tapestry of atoms or molecules, arranged in a precise, orderly pattern. This arrangement creates a rigid, three-dimensional grid that holds its structure with remarkable stability. The beauty of this organization is that it remains consistent over extended periods, almost as if it were frozen in time. Each type of crystal has its own unique pattern, determined by the nature of the atoms involved and their interactions. These intricate designs can be likened to a gentle melody, where each note is a specific atom positioned perfectly within the larger composition. This orderly repetition ensures that the crystal retains its form, untouched by transient influences around it. The steadfastness of this grid provides a sense of harmony within the crystal itself, echoing the laws of nature that govern its existence. Even as years pass and environments shift, the internal structure remains firm and unwavering, a testament to the enduring nature of these natural formations. Within this tranquility, the crystal exists in a state of continuous calm, poised to embrace each moment as it unfolds into the serene tapestry of time. Within the realm of crystals, quartz stands out as a remarkable example of abundance and durability. The strong framework formed by silicon and oxygen atoms creates a resilient structure that can withstand the test of time. This unique arrangement allows quartz crystals to endure the forces of erosion and weathering, often remaining intact for millions of years. Their composition makes them resistant to chemical reactions and physical wear, helping them retain their clarity and form despite the elements that surround them. As ancient sedimentary rocks evolve over vast geological timescales, quartz is frequently found nestled within them, a silent witness to the passage of time. The slow processes of nature cannot easily alter their steadfast presence, allowing quartz to bridge the ancient world with the present. In this way, the enduring nature of quartz crystals serves as a reminder of the strength found in their orderly structures. Each crystal, with its elegant clarity and resilience, carries the stories of the Earth's history within its facets, quietly contributing to the complex tapestry of the natural world. Deep within the Earth, certain crystals possess magnetic properties that allow them to engage with the planet's gentle magnetic field. This interaction, though often subtle, plays a significant role as time unfolds. As rocks are formed, these magnetic mineral crystals begin to align themselves in response to this magnetic influence. This alignment process occurs gradually, carefully guided by the invisible forces surrounding them. As layers of sediment settle and solidify over eons, the magnetic minerals nestled within find their orientation influenced by the Earth's magnetic field. This delicate interplay contributes to the way these rocks may record the magnetic history of the planet, capturing moments in time that stretch back millions of years. This slow dance between the magnetic properties of crystals and Earth's magnetic field reveals a hidden layer of connection to our world, illustrating a quiet harmony existing beneath the surface. The ongoing interactions continue timelessly, marking the subtle influence of nature's forces on the materials that compose the Earth. Each crystal holds the potential for stories waiting to be uncovered, existing harmoniously within the ebb and flow of time. As rain falls softly from the sky, it collects carbon dioxide from the atmosphere. This interaction gives rainwater a gentle acidity. Over long periods, this slightly acidic rainwater interacts with the surfaces of many crystals. This process, known as chemical weathering, unfolds at a very slow pace, often spanning thousands of years. As the rainwater seeps into crevices, it begins to dissolve the outer layers of the crystals, gradually softening the once sharp edges. The relentless movement of rainwater nurtures a transformative process, creating surfaces that appear rounded and pitted. Those edges that were once defined now become smooth and gentle, reflecting a natural ebbing away of the harshness once present. This quiet erosion occurs almost imperceptibly, a reminder of the soft strength found in nature's cycles. The crystals, enduring their slow transformation, continue to hold the essence of their origins within, slowly becoming altered yet remaining steadfast in their existence. Each subtle change adds to their story, inviting the unhurried passage of time to shape them further. When sunlight bathes crystals over long stretches of time, it gently interacts with their surfaces. The energy carried by light penetrates the crystals, reaching the chemical bonds that give them their vivid colors. This interaction, while subtle, can lead to a gradual fading of these hues. As decades turn into centuries, the impact of sunlight and air begins to take its toll. The once vibrant red or deep blue tones may soften into paler shades, almost as if the crystals are quietly whispering their stories of time. While the core structure of the crystal remains largely unchanged, its outward appearance transforms, becoming a reflection of the passage of light and life around it. This change unfolds imperceptibly, a slow dance of energy and matter. Each fading color hints at the whispers of history, the quiet moments held within the crystal's depths. As this process continues, the crystals stand resilient, forever holding the essence of their vibrant past, while adapting gently to the world around them, their softness becoming a serene part of their journey through time. The Earth's magnetic field is a dynamic feature, shifting gently over vast periods of time. Occasionally, the north and south magnetic poles undergo a gradual reversal, a process that unfolds slowly and takes thousands of years to complete. This transition is not governed by a precise schedule, but seems to occur in response to the Earth's internal dynamics. Every few 100,000 years, this natural cycle of reversal may take place, with the poles slowly exchanging their positions. Scientists find evidence of past reversals in the alignment of minerals found in ancient rocks, where tiny crystals, locked in place as they cool, record the direction of the magnetic field at that time. Throughout this process, the overall structure of the magnetic field remains intact, while its orientation changes. This gradual shifting can influence the planet's environment, though the nuances of those impacts stretch far beyond immediate understanding. The magnetic field acts as a protective barrier, shielding the Earth from cosmic rays and solar winds, while the rhythms of its reversals weave through the tapestry of our planet's long history, quietly reflecting the beauty of natural cycles. Crystals form through a gradual process, taking shape as atoms and molecules arrange themselves in ordered patterns. However, some crystal structures can find themselves in unstable configurations when exposed to specific temperatures and pressures. This instability can cause stress within the crystalline lattice, leading to a quiet transformation over long periods of time. As the environment surrounding these crystals changes, the atoms may begin to shift, seeking a more stable arrangement. This process unfolds gently, sometimes taking millions of years, as the crystal seeks to minimize its energy and reach a more favorable form. Gradually, the arrangement of atoms realigns, allowing new structures to emerge that are more stable under the current conditions. This delicate dance of reorganization continues in the deep earth, where temperature and pressure fluctuate in complex ways. The results of such transitions may be seen in a variety of minerals that reveal the history of the geological environment they once inhabited. In this slow, silent evolution, the world beneath our feet carries a timeless story of change. revealing the intricate balance that governs mineral stability and transformation. Deep within the earth, crystals find themselves surrounded by layers of rock and mineral, often far removed from the light of the surface. In this hidden world, they are subject to slow changes over immense spans of time. Within their atomic structure, certain isotopes may undergo a process called radioactive decay. This occurs at a consistent rate, releasing tiny amounts of energy as the atoms transform into different elements. This gentle release of energy can interact with the structure of the surrounding crystal lattice. As time unfolds, this internal bombardment creates subtle disturbances in the arrangement of atoms. Crystals, while appearing stable on the outside, are influenced by these minute changes. Over eons, the lattice may adjust, adapting to the energy being released from within. The shifts are extremely slow and often imperceptible, reflecting a dance of energy and matter that shapes the crystal over geological time. This continuous process contributes to the intricate and complex inner world of crystals, illustrating how even the smallest changes can leave lasting impressions on their structure. As this quiet transformation unfolds, it beckons further exploration into the mysteries hidden deep beneath the Earth's surface. Beneath the surface, metallic crystals like gold and platinum exhibit remarkable resilience against the forces of oxidation and corrosion. Their sturdy internal structure is supported by the electron C model, which describes how electrons are not bound to individual atoms, but move freely throughout the crystal. This communal sharing of electrons creates a strong bond that envelops each atom, contributing to the stability of the entire crystalline form. As these metals reside deep underground or within various geological formations, they remain largely untouched by external elements. This stability allows them to retain their elemental structure over incredibly long periods. The gentle embrace of their atomic arrangement ensures that interactions with environmental factors, such as moisture or atmospheric elements, are minimized. Each tiny fluctuation in the surrounding environment holds little sway over the crystalline integrity of these metals. They persist in their pristine state, resilient and enduring, forming a picture of durability within the ever-changing landscape of Earth. The subtle interactions that shape their environment occur at a pace so slow, revealing a lasting charm that continues to unfold quietly in the depths of the Earth. A calm sense of continuity lingers, suggesting there are more secrets waiting to be discovered within these alluring metallic formations. Within the heart of a crystal, internal layers exist in a serene arrangement, each one flat and parallel to the next. These layers are like sheets stacked with precision, creating a harmonious structure that offers stability and order. Each plane is filled with atoms organized in a meticulous fashion, providing a sense of balance that permeates throughout the entire crystal. This planar organization allows the crystal to exhibit consistent physical properties. As layers assemble, their flatness supports a strong bond between the atoms, holding them firmly in place. The regularity of this alignment endows the crystal with a smooth surface that can reflect light gently, creating a soft glow when observed. In contrast to the chaotic bustle of the world outside, these internal layers offer a calm and steady presence, untouched by fleeting disturbances. Over time, the arrangement of these layers ensures that the stability remains. In fact, even as they endure the slow processes of nature, their structure remains resilient and intact. The tranquil, orderly nature of these crystalline layers invites a sense of peace, symbolizing an eternal stillness that quietly exists, ready to share more of its secrets in an ever-unfolding journey. Within the atomic lattice of a crystal, imperfections exist, tiny variations that interrupt the otherwise perfect alignment of atoms. These imperfections allow the crystal to hold stored elastic energy, a gentle tension that quietly resides within. As this energy remains captured, the structure of the crystal maintains its calm, organized layers, preserving its serene appearance. Over time, this stored energy can gradually be released. As it escapes, subtle changes occur within the crystal. These shifts are often imperceptible, a soft evolution rather than a sudden transformation. The layers might ever so slightly adjust, allowing the atomic planes to realign and refine their stability. This slow, ongoing process highlights the crystal's ability to adapt quietly to the surrounding environment. As these structural changes unfold, the crystal continues to embody a sense of stillness and resilience. The interplay of energy and atomic arrangement reflects a deep and soothing balance, whispering of a dynamic world that thrives even in stillness. The journey of these internal energies within the crystal gracefully invites contemplation, resting like a gentle lullaby in the vastness of a calm universe. Crystalline materials possess a characteristic tensile strength, a limit defined by the strength of the chemical bonds that connect the atoms within. These bonds can withstand forces, holding the atoms in their delicate arrangement, yet they are not infinite. Each bond, crafted by the interplay of electrons, contributes to the overall stability of the crystal. When stress is applied, the atomic structure responds, but only up to a certain point. When the applied force exceeds this tensile strength, the bonds may begin to break, leading to imperfections or fractures. This threshold serves as a reminder of the intricate balance within the crystal. As each bond stretches and ultimately reaches its limit, it quietly tells a story of resilience and fragility. The arrangement of atoms reflects a unity that can yield under pressure, but until that moment, the crystal stands firm, radiating tranquility. The properties of these bonds evoke a captivating harmony, a gentle reminder of how nature finds equilibrium within the constraints of itself. This deep-rooted connection fosters a sense of stability that underlines the existence of crystals, slowly vibrational yet profoundly resilient. In their steadfastness, they embody a serene existence, continuing their calm presence, ever ready to interact with the world around them. Acidic groundwater, moving gently through rock, can create subtle changes in crystalline structures. Over time, this slow seep can interact with minerals, leading to a gradual etching of the crystal surface. The water, slightly acidic from natural processes, delicately dissolves certain components, revealing the beauty hidden within. As the liquid travels, it finds paths through the rock, slowly sculpting intricate patterns on the crystals. These patterns emerge, not forcefully, but as a natural consequence of the slow and patient interaction between the water and the mineral surface. Each droplet carries the potential to unlock new shapes, creating a canvas of soft lines and textures, unique to each crystal. The process unfolds over long periods, a testament to the gentle power of nature. These patterns tell a story of time, patience, and fluid movement. They are reminders of the ongoing transformations occurring even in the quietest places. With each passing moment, the crystals bear witness to the world around them, continuing their graceful presence, subtly reshaped yet always splendid in their form. Bismuth crystals, in their unique formation, can display a mesmerizing array of iridescent colors. This visual phenomena arises from a process known as thin film interference, which occurs when layers of light interact. As light gently strikes the tiny oxide layer covering the crystal, it reflects off both the top and bottom surfaces of this layer. Each reflection creates a slightly different path for the light waves, which then combine in various ways. Depending on the angle of observation, certain colors are enhanced while others are diminished, resulting in a soft shifting spectrum. The colors can seem to dance across the surface, creating a captivating visual display that changes with light and perspective. This natural occurrence demonstrates the delicate balance of physical properties at play within the crystal. Each iridescent display tells a story of light interacting with matter, forming patterns that are ever-changing, yet beautifully consistent. As the light whispers across the surface, the crystal remains a quiet emblem of nature's artistry, patiently revealing its colors in a gentle, fluid dance. Continental drift is a continuous process that unfolds over millions of years, gently shifting land masses across the Earth's surface. This slow movement, driven by the dynamics of tectonic plates beneath, leads to the gradual rearrangement of coastlines and mountain ranges. Each movement, though it may seem negligible in a short span, accumulates over ages, sculpting the landscape in ways that might surprise the observer. As continents drift, they reshape the very contours of the planet. Land masses collide, pull apart, or slide against each other, leading to the formation of new geological features. Mountain ranges rise as tectonic plates push against one another, while coastlines retreat or extend, creating new shores where once there were none. This dance of the continents also influences climate patterns, as the positioning of land and ocean alters wind and current flows. Over extensive timescales, the shifting of these vast platforms impacts ecosystems and weather systems in subtle but profound ways. The Earth continues its quiet transformation, with each movement telling a story of time and change, ready to unfold into the future. A rare and fascinating phenomenon called photochromism exists within certain crystals, captivating those who study their unique properties. In these remarkable materials, exposure to light brings about a reversible change in color, transforming their appearance in a delicate and temporary manner. As light interacts with the atomic structure of the crystal, it initiates a shift that alters how the crystal absorbs and reflects light. When illuminated, the crystal may display vibrant hues or gentle shades that were not present before. This transformation occurs as energy from the light alters the arrangement of atoms or molecules within the crystal lattice. The change is not permanent. Once the light source is removed or sufficiently altered, the crystal gracefully returns to its original color, quietly resuming its previous state. This dance of light and color occurs on a scale that is hard to appreciate in the hustle and bustle of daily life. Yet, within these crystals, a world of subtle beauty and change exists. Every shift is a reminder of nature's exquisite complexities. The stillness remains, inviting further exploration into these wonders of light. When a crystal cools from its molten state, a fascinating transformation begins to unfold. In this cooling process, the material transitions from a viscous liquid to a structured solid. As the temperature decreases, the atoms or molecules within the crystal begin to arrange themselves into a well-defined lattice structure, laying the foundation for its eventual form. However, this cooling is not uniform. Variations in temperature can lead to uneven contraction, creating internal stresses within the crystal. These stresses may remain hidden for some time, waiting silently as the crystal stabilizes. Over time, if these internal forces become significant enough, they can lead to fractures. Remarkably, these cracks can appear even in the absence of any external force, as the accumulated tensions seek a way to release themselves. The delicate balance of pressures within the crystal is a testament to the intricate behaviors of materials as they transition through different states. Understanding this process reveals the quiet complexities that exist within crystals, inviting a deeper appreciation for their natural formation. Amidst the stillness of their structure, the story of their growth continues, ready to unfold further. In varied environments, the journey of a crystal does not truly end after its formation. Over thousands of years, it may slowly begin to absorb gases from the atmosphere. This process occurs much like a gentle whisper as the crystal interacts quietly with the world around it. As these gases penetrate the crystalline structure, they find their way into the spaces of the lattice, seamlessly integrating into the existing arrangement of atoms or molecules. This gradual absorption can introduce subtle changes within the crystal's structure. Each gas molecule that becomes trapped adds a layer of complexity. It shifts the delicate balance of forces within, altering the crystal's internal dynamics. These changes are often imperceptible, unfolding over vast stretches of time, contributing to a deeper story of the crystal's evolution. The interplay between the crystal and its environment reflects a continuous cycle of interaction. With each moment, each breath, the crystal becomes a little different, a quiet testament to the passage of time. These slow transformations invite a sense of wonder as the crystal quietly holds the history of its surroundings within its enduring form, poised to continue its silent journey through the ages. In a perfect crystal lattice, the arrangement of atoms is a harmonious and stable structure. This ordering contributes to a density that remains largely constant over time, creating a solid foundation for the crystal's existence. As the atoms settle into their precise positions, they form an orderly pattern, producing a sense of balance within the crystalline form. However, within this perfection, subtle imperfections can emerge. When impurities or defects are introduced into the lattice, the uniformity begins to shift. These irregularities might alter the density ever so slightly. As a result, the crystal may gently respond to its environment, particularly when exposed to extreme temperatures or pressures. In such cases, the lattice can experience minute changes, allowing the density to adapt gradually. These variations unfold slowly, often taking years to manifest. Though delicate, they add an intriguing layer to the crystal's identity. Over time, the fixed nature of the perfect lattice remains the core essence, while these small fluctuations whisper stories of change. The crystal continues its tranquil existence, a silent witness to the passage of time, ready for whatever comes next. The movement of tectonic plates beneath the Earth's surface generates powerful shear forces. These forces exert enormous pressure on rock formations, often causing large crystal lattices to shift and slide past one another. Over millions of years, this gradual slippage unfolds quietly and steadily, creating intricate changes in the structure of the Earth. As the crystals within these lattices interact, the alignment can become distorted, leading to the formation of faults. These faults represent the points where the crystal structures have overcome their internal cohesion, yielding to the persistent forces around them. The deformation of rock crystals is an ongoing process, a gentle dance that reshapes the Earth's crust over a vast timescale. Each movement, although imperceptible in the moment, contributes to a larger narrative written in stone. The crystalline structures adapt and evolve, reflecting the dynamic nature of the planet. Through these slow transformations, the Earth's geology is woven into a complex tapestry, ever-changing yet steadfast. An openness to these continuous movements feels comforting, a reminder of the vast, patient rhythms of the natural world. Certain crystals hold a hidden tension within their structures, an internal strain emerging from the differing rates of thermal expansion among their constituent atoms. This occurs because the various atoms react differently to changes in temperature, with some expanding or contracting at rates that do not fully align with those of their neighbors. Over time, this discrepancy creates a delicate balance within the crystal lattice, storing energy like an unseen reservoir. As the temperature fluctuates, the internal strain can become significant. This energy may not be instantly released. Instead, it resides quietly, waiting. Gradually, the stored strain can lead to slow, subtle changes in the crystal's form. Cracking or warping may occur, appearing almost imperceptibly at first. Yet over long stretches of time, these changes accumulate and transform the crystal's integrity. This patient unraveling speaks to the enduring nature of such materials, highlighting the intricate dance of atomic forces at play. It reminds us that beneath still surfaces, a world of dynamic interactions quietly shapes the reality we observe. As these processes continue in their measured way, the relationships between atoms evolve, further enriching the complex story of crystals. The soothing rhythm of these transformations flows seamlessly onward, inviting a sense of calm and connection to the Earth's natural wonders. Within the tranquil depths of a crystal, a slow dance of atoms unfolds over eons. Elements that form the structure can gradually diffuse, moving ever so slightly through the crystalline lattice. This movement often occurs at an imperceptible pace, as neighboring atoms gently swap places, allowing for a subtle rearrangement of the material's internal order. Even though the overall crystal structure may appear unchanged, this delicate atomic exchange can lead to slight modifications in its chemical composition. As atoms shift, the properties of the crystal can alter in quiet ways. These changes may influence aspects such as the crystal's color or how it interacts with light, all while maintaining a core resemblance to its original state. This slow metamorphosis underscores the dynamic nature of crystals. They exist as living records, shaped by the passage of time and the movement of their own building blocks. Each subtle transformation adds depth to their story, a gentle reminder of the profound processes at work beneath the surface. The simplicity and tranquility of these changes resonate softly, connecting the crystal's existence to the slow rhythms of nature itself, inviting quiet contemplation and restful thoughts. A crystal exists in a world where time stretches, allowing for a gentle growth that is almost imperceptible in the moment. Surrounding it are dissolved minerals, suspended in water, quietly waiting to find their place. As conditions align, these tiny particles begin to deposit onto the surface of the existing crystal. Layer by layer, they adhere smoothly, enhancing the crystal's form. This slow addition creates a rhythmic expansion, gradually increasing its size, like a whispered promise of transformation. Each new layer forms with precision, merging seamlessly with the crystalline lattice, preserving the integrity of the structure while inviting change. Over many years, this process can lead to crystals that are much larger than they were when they began their journey. Yet, the growth is subtle, embodying the essence of patience. At each stage of this quiet accumulation, the crystal remains a steadfast testament to the slow, deliberate forces of nature. This ongoing transformation fosters a soothing sense of continuity, reminding us of the calm processes at play in the world around. The gentle unfolding of growth invites peaceful contemplation as each moment of change contributes to a larger story. Within the depths of the earth, immense pressure builds, exerted by tectonic forces that shape the landscape over countless years. Crystals, formed in more tranquil settings, find themselves caught in this relentless embrace. Under such pressure, the stability of their structures is tested. The forces at play can lead to subtle deformations, bending the crystal lattice in ways that alter its original shape. In some instances, this pressure becomes too great, and the crystal may fracture, leading to the emergence of new forms. This transformation does not halt their existence, but instead ushers in new possibilities. Over time, these changes give rise to metamorphic rocks, where the original minerals and crystals undergo profound alterations, resulting in the creation of new crystal types under the ever-shifting conditions deep within the earth. This quiet dance of pressure and change unfolds slowly, reflecting a hidden world of transformation that occurs beneath our feet. Each crystal carries a story of resilience, adapting to its environment through eons of geological activity. The serene cycles of formation and metamorphosis hint at the intricacies of natural processes, a gentle reminder of the dynamic forces shaping the earth itself. Calmly, these changes weave a tapestry of creation, inviting reflection on the processes that persist, often unnoticed beneath the surface. Within certain crystals lies a remarkable property known as the piezoelectric effect. When these specific crystals experience mechanical stress, such as being squeezed or subjected to pressure, they respond by generating an electric charge. This fascinating transformation takes place as the internal structure of the crystal shifts slightly under the influence of the applied pressure. As the internal arrangements of atoms and molecules are altered, they create an imbalance that produces electrical potential energy. This interaction occurs without any outside influence or need for additional energy sources. It is an intrinsic quality of the crystal's arrangement and bonding. The process is subtle and peaceful, reflecting the gentle way in which crystals respond to the forces acting upon them. The electrical energy derived from such stress can fluctuate in proportion to the level of pressure applied. In this way, the piezoelectric effect illustrates an intimate connection between mechanical dynamics and electrical behavior within certain crystal structures. This ongoing interaction in the world of crystals is a testament to the complex relationships that govern natural phenomena. As layers of pressure dance with delicate shifts in atomic arrangements, the crystals remain quietly resilient, responding in ways that underscore the beauty of their inherent properties. It invites thoughts of how the world is continuously in motion, even in forms we may not see or fully understand. Within the realm of certain crystals lies the intriguing behavior of magnetoelectric materials. These unique crystals possess the ability to intertwine their electric and magnetic properties in a gentle dance of interaction. When an electric field is applied to these crystals, they respond with a corresponding magnetic effect. This reciprocal relationship illustrates a harmonious balance in their internal structure, where the arrangement of atoms and the bonding between them create this delicate coupling. The magnetic response arises smoothly as the energy from the electric field aligns the magnetic dipoles within the crystal. Conversely, introducing a magnetic field can also induce an electric polarization, demonstrating the elegant way these properties influence one another. This complex interplay highlights the interconnectedness in nature, revealing how changes in one aspect can resonate through to affect another. With their ability to seamlessly transition between electric and magnetic states, magnetoelectric crystals stand as a quiet reminder of the subtleties of physical systems. Each layer of interaction unfolds softly, embodying a serene world where energy flows in silent harmony, offering a glimpse into the intricate balance that characterizes these fascinating materials. As the night moves on, the understanding of this interplay deepens, inviting thoughts of the gentle mysteries still to explore. Within the structure of some crystals, one may find tiny imperfections that disrupt the otherwise perfect arrangement of atoms. These imperfections, known as defects, can take various forms, such as missing atoms or atoms occupying positions they do not perfectly belong to. Even though they might be considered flaws, these defects are often stable, becoming a lasting part of the crystal's identity after its formation. Over time, these tiny anomalies can create pathways for movement within the crystal lattice, influencing the way energy flows through the material. Each defect tells a quiet story of the conditions present during the crystal's growth, revealing the environments that shaped its formation. The arrangement of atoms surrounding these imperfections can adjust to accommodate them, leading to unique characteristics within the crystal. These subtle irregularities embody a delicate balance between order and chaos, enhancing the diverse properties found in crystalline materials. The existence of defects allows for variations that can be quietly intriguing, underscoring the complexity of these natural structures. As we ponder the intricate nature of these crystals, their silent stories unfold softly in the stillness of the night, inviting moments of reflection and wonder. Crystals have a special quality known as pleochroism, where they reveal different colors depending on the angle from which they are viewed. This intriguing phenomenon arises because the crystal interacts with light in a unique way along each of its crystallographic axes. Light journeys through the crystal, encountering varying arrangements of atoms that can absorb certain wavelengths while allowing others to pass through. As light travels, it dances through the structured lattice, and different colors emerge based on the pathway it takes. In some orientations, a crystal might shimmer with warm hues, while in others it transforms, displaying cooler tones. This captivating shift in color occurs without any change to the crystal itself, as its internal structure remains constant. Such variations can bring a sense of peace as one observes how the crystalline form interacts with the surrounding light. Each perspective offers a gentle reminder of the complexity woven into the natural world. The subtle beauty found in these shifts creates a serene atmosphere, encouraging quiet contemplation as one gazes upon these marvelous structures. As night deepens, the crystals continue to harmonize with the whispers of light, revealing their quiet secrets in a soothing dance. Crystals resting on the surface of the earth undergo a gentle transformation over long stretches of geological time. When exposed to wind and rain, their once smooth surfaces begin a slow process of wearing away. The force of the wind carries tiny particles that dance around the crystals, gradually chipping away at edges and corners. Meanwhile, rainwater, with its soothing patter, interacts with the crystal's surface, dissolving minerals and causing tiny splits that further contribute to erosion. This continuous, soft abrasion leads to the gradual reduction of the crystal's size, creating smaller fragments that scatter across the landscape. Each drop of rain and gust of wind contributes to this quiet symphony of change, reshaping the crystals without haste. Over countless years, these natural forces create smoother, more delicate shapes, each telltale mark revealing a history of their journey through time. As they weather in this way, the crystals hold on to the stories of their formation and transformation. They become a part of the Earth's ever-evolving narrative, finding beauty in their gentle decay. In a serene embrace of time, these prisms of light reflect a world that is continuously reshaping itself, inviting quiet reflections of nature's slow, graceful rhythms. Within the crystal lattice, a delicate arrangement of atoms is held together by bonds that possess certain strengths and characteristics. These bonds determine how rapidly mechanical vibrations, known as phonons, can move through the crystal. As these vibrations occur, they ripple through the structured framework, much like sound waves traveling through air or water. The speed of these phonons is influenced by the spacing between the atoms, which creates a specific pathway for the vibrations to follow. The closer the atoms are to each other, the more easily they can transfer energy, allowing vibrations to travel quickly. Conversely, wider spacing can slow down this movement. Thus, the unique structure of each crystal governs the rate at which sound-like vibrations can propagate. This intrinsic property emerges from the very nature of the material itself, reflecting the strength and arrangement of the atomic bonds. As phonons weave their way through the crystal, they carry energy, and their interactions can lead to an array of effects, quietly influencing the crystal's overall behavior. Through time, the journey of these vibrations paints a soft picture of how the crystal exists in its world, quietly resonating within its own serene environment, open to the gentle dance of energy that fills its structure. In the serene world of crystals, size is not boundless. Each crystal grows from the careful arrangement of atoms that align in a distinctive pattern. This growth is delicately influenced by the availability of materials that surround it. As atoms gather to form larger structures, they interact with one another, dancing into place within the nutrient-rich environment. However, the forces of nature, such as gravity and surface tension, gently guide this process, imposing limits on how large a crystal can become. When a crystal reaches a certain size, these forces may create a delicate balance that begins to waver. The weight of the crystal can lead to stress within its structure, while surface tension pulls at the edges, making it prone to instability. At this point, any further growth may lead to not expansion, but fragmentation, as the crystal breaks apart under its own weight. This natural process ensures that while crystals can become quite spectacular in size and form, they remain harmoniously bound by the laws of nature. As they grow and eventually face their limits, they tell a gentle story of balance and beauty, quietly reflecting the intricate relationships within their own world. Within the tranquil architecture of crystals, certain elements possess a unique characteristic known as radioactivity. These radioactive elements exist quietly within some crystal structures. Over time, they undergo a gradual transformation, decaying at a predictable rate. This decay is a subtle, ongoing process where the original atoms slowly shift into new isotopes. As this change occurs, the very essence of the crystal begins to change, quietly altering its chemical signature, layer by delicate layer. Each transformation unfolds like a gentle whisper in the fabric of time, reflecting a rhythm that speaks to the stability and instability intertwined in the life of a crystal. The original element, as it transforms, leaves behind traces that can be studied, hinting at the history of the crystal and the environment in which it formed. This slow dance of decay reminds us of the passage of time that defines so many aspects of nature, weaving together a narrative of rest and renewal. The quiet evolution continues, patiently marking the cycles of existence within the heart of the crystal, offering a glimpse into the ever-changing nature of the elements themselves. In the serene nature of piezoelectric crystals, there lies a fascinating phenomenon known as the converse piezoelectric effect. When an electric field is applied to these crystals, they respond by undergoing internal mechanical strain. This response is not abrupt. Rather, it unfolds gently, like a soft adjustment within the crystal structure. As the electric field interacts with the atomic arrangement, the crystal subtly stretches or compresses, storing mechanical energy in the process. This stored energy exists quietly, waiting to be released or transformed into another form. The relationship between electricity and mechanical strain within these crystals illustrates a harmonious balance within their internal structure. Each adjustment reflects the delicate nature of molecular interactions, subtly altering the positioning of atoms and bonds just enough to create a new state. The interplay between electric fields and mechanical properties engraves a silent story into the fabric of these crystals, showcasing their ability to adapt and respond to external influences. With each moment, the crystal holds onto this mechanical energy, a reminder of the intricate connections that govern its existence, inviting further exploration and understanding. The intricate world of crystals reveals an interesting characteristic regarding their interaction with heat. Crystals, depending on their unique composition and structural arrangement, possess the ability to either absorb or reflect heat in varying degrees. This capacity influences how they respond to their environment, particularly over extended periods of exposure to fluctuating temperatures. Each crystal behaves in a manner reflective of its internal structure and the bonds that hold its atoms together. As temperatures rise and fall, the thermal energy interacts with the crystalline lattice, gently nudging atoms from their positions within the structure. This ongoing dance of heat can lead to subtle changes over time. In certain conditions, the stress induced by temperature variations may slowly contribute to weathering. The once sturdy formations may begin to fragment, their edges becoming less distinct as they respond to the continuous shifts in thermal energy. As these changes unfold, the larger crystal formations may break down gradually, revealing the complexities of their internal makeup. This quiet transformation echoes the delicate balance of forces that govern not only the life of crystals, but also the landscapes they inhabit. Each shift in temperature plays a role in telling the timeless story of these remarkable structures. Within the serene layers of the earth, some minerals experience the gentle forces of heat and pressure over extended periods. This prolonged exposure can lead to a fascinating process known as recrystallization. As the original crystal feels the warmth enveloping it, its internal structure begins to shift. The heat allows the atoms within the crystal to gain energy, creating movement. This movement leads to the gradual dissolution of the original crystal as it transforms under these changing conditions. During this transformation, the atoms reconfigure themselves, coming together to form new crystalline structures. While these new crystals may often be smaller, they tend to display greater stability than their predecessors. The shape of the original crystal fades away, replaced by the subtle beauty of new formations. This quiet metamorphosis signifies a continuous cycle of change that resonates deeply within the planet's crust. As these transitions occur, they serve as a reminder of the patience inherent in the natural world, marked by the slow yet persistent evolution of minerals over time, a calm dance of atoms and energy that echoes throughout the layers beneath our feet. In the tranquil world of crystals, light journeys through their forms with a unique grace. Each crystal possesses a refractive index, which measures how much light bends as it passes through. This bending occurs because of the crystal's internal structure and the density of its electrons. The intricate arrangement of atoms within the crystal allows light to interact in specific ways, causing it to slow down and change direction. However, there exists a physical upper limit to this refractive index, rooted in the properties of the crystal itself. This limit arises from the density of electrons surrounding the atoms, which influences how light interacts with the material. Crystals with higher electron densities can bend light more dramatically, reaching towards their maximum potential. Yet, even in this expansive realm of possibilities, there remains a threshold that cannot be crossed. As light flows through each crystal, it reveals the delicate balance of nature's design, illustrating a perfect harmony between structure and the behavior of light. In this quiet coexistence, the crystals stand, reflecting and refracting the world around them, a gentle reminder of the beautiful limitations that govern their behavior. In the serene realm of thermotropic liquid crystals, a captivating transformation occurs in response to temperature changes. These materials possess the remarkable ability to shift their phase from solid to liquid crystal and then to a fully liquid state. This transition is accompanied by significant alterations in their optical properties, gently influencing the way light interacts with them. At lower temperatures, the molecules within a thermotropic liquid crystal are closely aligned, presenting a stable structure that allows some optical clarity. As the temperature rises, these molecules begin to gain energy, transitioning into a more fluid arrangement. In this liquid crystal state, they can manipulate light more dynamically, opening up a spectrum of possibilities for how it is transmitted and reflected. As the heat continues to rise, the molecules eventually break free from their ordered alignment, resulting in a liquid phase. Throughout this process, the smooth flow of light becomes a dance of changing patterns and reflections. This natural behavior, based solely on temperature variations, showcases the intricate balance within the material itself, revealing a hidden harmony governed by physical laws. Each phase's delicate interplay reflects a world of transformation, gently inviting the mind to explore the wonders of thermal dynamics as the night continues on. Beryl crystals, such as emerald and aquamarine, embody a remarkable stability within their internal structure. This stability arises from a precise arrangement of beryllium and aluminum atoms, intricately interlinked with silica tetrahedra. These connections create a resilient lattice, allowing the crystals to withstand the slow, relentless forces of their surroundings. In the depths of the earth, where conditions are stable and geological processes unfold over immense time, beryl crystals endure. They resist degradation, remaining intact as the world above them changes. This durability allows them to thrive in igneous and metamorphic rocks, where they may exist for eons, slowly forming and developing their vibrant colors. Emerald, known for its deep green hue, and aquamarine, with its calming blue tones, both represent the beauty that can emerge from such sturdy molecular arrangements. Each crystal reflects the long journey of its formation, capturing the essence of the elements that created it. In this tranquil existence, beryl crystals continue to embody the patience of nature, remaining ready to share their story as the layers of time unfold softly around them. The rise and fall of sea levels occur as a gentle, unhurried rhythm, shaped by the interplay of global ice volume changes and tectonic activity beneath the Earth's surface. These fluctuations are reflectively gradual, unfolding across thousands of years, quietly sculpting the contours of coastlines. As ice melts and glaciers retreat, water flows back into the oceans, nudging the sea levels higher. In contrast, during colder epochs, when ice expands, the water recedes, revealing land that has long been hidden beneath the waves. This slow dance alters not just the immediate shoreline, but the larger landscape nearby, with entire ecosystems adapting to the shifting boundaries of land and sea. The geological forces at work beneath the surface also contribute to these changes, as tectonic movements can raise or lower the land itself. Over millennia, these combined effects can create new coastal features, transforming familiar shores into something entirely different. With each ebb and flow of the ocean, the landscape evolves, patiently reminding us of the Earth's enduring and dynamic nature, inviting us to contemplate the unceasing change all around. The melting point of a pure crystalline solid presents a serene and stable temperature at which its organized lattice structure begins to surrender. At this moment, orderly arrangements of atoms and molecules gently yield to the allure of fluidity, marking a transition from solid to liquid. This temperature is a fundamental characteristic of the substance, uniquely tied to its composition and crystalline arrangement. In the presence of impurities, this purity is disrupted, often resulting in a lower melting point. The mixture becomes less predictable as foreign particles introduce new interactions within the lattice. External pressures can also play a role, subtly nudging the melting point higher or lower, demonstrating how delicate the balance can be within nature's structures. This intricate interplay of conditions reflects the essence of materials, revealing how even their physical properties are adaptable to both their environment and composition. The transformation from solid to liquid unfolds gradually, providing a gentle reminder of the deep and consistent laws governing matter as the world around us continues its unhurried dance of change. Certain crystals, such as quartz, experience a slow and gradual dissolution when in contact with water over extensive periods. This process is gentle and subtle, occurring so slowly that it often goes unnoticed. As water interacts with the crystal's surface, tiny amounts of its material are carefully eroded away, resulting in a delicate transformation of size and shape. The crystal's structured lattice, once solid and defined, begins to soften as individual particles yield to the embracing flow of water molecules. This change is not abrupt, rather it unfolds over eons, reflecting the inherent dynamism of these natural forms. The smooth surfaces and corners of the quartz may slowly round, leading to an evolution in its appearance. Such gradual shifts remind us of the persistent influence of seemingly gentle forces, as water carries away the minuscule fragments, gradually reshaping the crystal without haste. The reflection of light through these altered surfaces continues to sparkle, a soft reminder of the beauty inherent in transformation. Each moment unfolds quietly, inviting contemplation of the slow rhythms of nature and the continuous change surrounding us. Under the influence of intense heat, crystals journey through a fascinating transformation. When temperatures rise significantly, the orderly arrangement of atoms that defines a crystal's structure begins to break down. This increase in energy allows the atoms to move more freely, disrupting their previous positions. As the crystal reaches its melting point, it transitions from a solid form into a liquid state, where the once rigid framework dissolves into a warm, flowing substance. When the heat subsides, a gradual cooling occurs. In this serene moment, the atoms slowly begin to regroup, finding new positions that can create distinct crystal structures. This process of rearrangement leads to the formation of new crystals, each with their own unique properties and characteristics. The transformation can yield a variety of forms, shimmering in light and reflecting different colors, which are shaped by the energy and environment surrounding them. Such a rhythmic cycle of melting and reforming captures the essence of change that permeates the natural world. The quiet transformations within crystals resonate with the soothing flow of time, inviting us to reflect on the beauty of renewal and the subtle power of energy in reshaping existence. The possibilities for these structures feel endless, gently suggesting the ongoing dance of nature as it unfolds softly in the background. Thermal conductivity, a defining feature of crystals, reflects their ability to transfer heat through atomic vibrations. In these exquisite structures, atoms are tightly arranged in a manner that allows energy to flow seamlessly. As heat is applied, these atoms begin to vibrate, passing energy from one to another in a calm, continuous manner. This process occurs steadily, maintaining a consistent level of thermal conductivity that characterizes the crystal itself. The value representing this property remains relatively stable, providing a sense of predictability. It is only under extreme conditions, such as significant changes in temperature or structural alterations, that this conductivity might shift. Prolonged exposure to high energy can alter the arrangement of atoms, thereby changing the pathways through which heat travels. When these energetic conditions are lifted, the crystal can return to its original state, re-establishing its familiar pattern of atomic vibrations. This gentle equilibrium within crystals serves as a reminder of the intricate balance present in nature. Each tiny vibration contributes to the harmonious flow of energy, emphasizing the quiet resilience of these structures as they adapt and continue their journey through time. Energy moves softly within, evoking a sense of calm as the cycle of thermal conductivity unfolds in soothing rhythm. Amethyst crystals, with their tranquil purple hues, emerge within the warm embrace of geodes. These unique structures, often formed in volcanic rocks, carry the echoes of time, sometimes dating back millions of years. Within these geodes, the conditions nurture the growth of amethyst, allowing it to develop slowly and steadily. The coloration of these beautiful crystals comes from tiny impurities of iron, which blend quietly into the otherwise clear quartz structure. This gentle infusion of color creates the stunning purples that so many find captivating. Yet, despite these variations, the quartz framework remains remarkably steadfast. Over the long durations that these crystals exist, they maintain a chemical stability that allows them to persist through ages, weathering the gentle passage of time while remaining largely unchanged. In the stillness of their existence, they stand as a testament to nature's ability to create intricate forms, enduring and serene. As the atoms within these structures vibrate softly, they tell a story of resilience, grounding themselves within the Earth's rich history, ready to unfold in their own quiet pace. Within the intricate world of crystal formation, a certain order arises, displaying the beauty of a crystal lattice in its well-defined arrangement of atoms. Each atom aligns itself in a precise repeating pattern, creating a structure that reflects harmony and symmetry. Yet, this order has its limitations. At the atomic level, even the most carefully formed crystals contain dislocations and impurities. These small disturbances create tiny breaks in the otherwise perfect lattice, reminding us that absolute flawlessness is a challenge that nature encounters. Each dislocation, while seemingly minor, plays a role in the overall structure, influencing how a crystal behaves and interacts with its surroundings. The presence of impurities, though sometimes seen as imperfections, can also contribute to the uniqueness of each crystal. These variations result in a rich diversity among crystals, allowing their forms to vary even within the same type. The delicate balance between order and disorder weaves a story of resilience and complexity, quietly highlighting the understated beauty found within these seemingly simple structures. As the atoms gently vibrate in their lattice work, they embody the essence of nature's intricate design, providing an endless source of contemplation and wonder. Orogenic cycles unfold slowly, a majestic unfolding of Earth's crust, where tectonic plates slowly move and interact over enormous spans of time. The collision of these massive landmasses creates upward forces that elevate vast stretches of rock, gradually forming mountain ranges. These processes, unfolding over tens of millions of years, reveal the power of nature as land rises in layers, creating peaks and valleys that become etched into the landscape. As mountains rise, they begin to shape the environment around them. Their towering heights influence local weather patterns, catching moisture-laden winds and creating rainfall on one side, while leaving the other side drier and more arid. This dynamic relationship between mountains and weather sets the stage for various forms of erosion, as water, wind, and ice work tirelessly to sculpt the land over eons. The resulting geological features tell stories of ancient forces and transformations, quietly inviting contemplation on the passage of time. With each gradual shift in the earth, the landscape continues to evolve, an endless cycle of formation and erosion blending into a serene, slow rhythm of change. Each mountain range stands as a reminder of the intricate dance of our planet, a process that connects the past with the present in a gentle, unfurling narrative. Extremely low temperatures introduce a different aspect to the behavior of crystals. As the temperature drops, the kinetic energy of the molecules within the crystal structure decreases significantly. This reduction in energy alters the vibrational patterns that help maintain the integrity of the crystal lattice. The once flexible bonds between atoms become strained, making the structure more fragile. In these colder conditions, certain crystals may lose their ability to absorb stress, becoming brittle and prone to fracture. This brittleness limits their operational range, as they cannot withstand forces they might have easily endured at higher temperatures. The very essence of their formation, a meticulous arrangement of atoms, shifts into a state where the slightest pressure could cause them to splinter or shatter. These changes underline the delicate balance within crystal structures, emphasizing how temperature can profoundly affect their properties. The transformation from a robust solid to a more fragile form speaks to the intricate dance of elements, quietly reminding us of the subtle influence of the environment on the natural world. The interplay between temperature and crystalline structure weaves a story of change, inviting wonder at how even the smallest shifts can redefine stability and strength in the realm of materials. Within the serene world of crystals, some structures possess internal planes of weakness, subtle variations in their organization. These planes arise from differences in atomic bonding, where certain connections between atoms are slightly less robust than others. This variation creates pathways that can guide the behavior of the crystal over time. When external stress is applied to a crystal, these weaker planes may serve as initiation points for fractures. Rather than breaking randomly, the crystal can follow these predetermined routes, leading to a more defined pattern of breakage. This phenomenon is part of the intricate balance within the crystal, as the structured arrangement of atoms not only defines strength, but also vulnerability. The presence of these planes adds to the complexity of the crystal's identity, shaping both its resilience and fragility. As time unfolds, the way these internal weaknesses interact with external forces tells a quiet story of change, illustrating how even within a seemingly solid form, there exists a delicate interplay of strength and potential compromise. This understanding encourages a gentle reflection on the layered realities within the natural world, each crystal a testament to its own history and character, revealing insights that linger in the stillness of time. At the heart of many crystals lies a core structure made up of what are known as unit cells. These unit cells serve as the fundamental building blocks of the crystal's architecture. Each unit cell is defined by a specific size and shape, remaining consistent throughout the entire crystal. This regularity lends a sense of harmony to the structure, creating an unbroken pattern that extends infinitely in 3 dimensions. The arrangement of these unit cells forms a symmetrical lattice, wherein each cell is precisely positioned in relation to the others. This orderly repetition contributes to the overall stability of the crystal, establishing a solid framework that can resist various external influences. As tensions arise, the cohesive strength of the unit cells plays a crucial role in preserving the integrity of the crystal. As time progresses, the interaction between these repeating units can influence the way the crystal responds to its environment. Changes in temperature, pressure, or even the surrounding atmosphere can affect how the unit cells maintain their orderly dance, whispering stories of resilience and adaptation. Each crystal, a unique reflection of its foundational structure, carries with it the essence of balance and continuity, quietly evolving within the gentle rhythms of the natural world, ever so ready to reveal more of its serene mysteries. The size of the unit cells within a crystal is intricately linked to the atomic radii of the elements that compose it. Each element possesses its own unique atomic structure, which defines how closely its atoms can be packed together. When a crystal forms, the atomic interactions configure themselves into a stable arrangement, resulting in unit cells that hold fixed dimensions. This unchanging size becomes a defining characteristic of the crystal, providing a fundamental unit of measurement that remains constant throughout the structure. Once established, these unit cells create a consistent blueprint, allowing for meticulous repetition and organization. This fixed size contributes to the overall stability and strength of the crystal, enhancing its ability to maintain order over time. As the surrounding environment influences the crystal, the dimensions of the unit cells remain stable, providing a sense of unyielding calmness amidst external changes. In this continuous dance of atoms, the harmonized nature of the unit cells quietly reflects the beauty of balance and equilibrium that echoes through the entirety of the crystal. This stability invites contemplation, stirring a gentle curiosity about the intricate patterns woven deep within, while softly hinting at the mysteries yet to be explored. The complex beauty of crystal structures often reveals fascinating intricacies, yet their existence is delicately balanced by thermodynamic stability. In essence, these intricate arrangements of atoms can only persist if they remain at a suitable energy level within their environment. Highly complex structures, with their numerous geometrical forms and patterns, may encounter challenges in maintaining their stability over time. If the energy within the system is not adequately sustained, the crystal may undergo changes, slowly rearranging itself into a lower energy state. This transition reflects a natural inclination towards simplicity and equilibrium, gently guiding the material back to a more stable configuration. In this quiet process, the original complex arrangement may fade, allowing room for more harmonious structures to emerge, resonating with a soothing sense of order. Thus, the world of crystals unfolds layers of complexity, yet remains tethered to this fundamental principle of stability. Each transformation speaks to the ongoing dance of energy within the system, revealing the delicate balance that governs its existence. In this gentle flow, the subtle shifts linger softly, inviting a sense of wonder about the ever-present cycles of change and stability. Deep within the Earth's crust, where time stretches infinitely, crystals quietly undergo transformations. As layers of sediment accumulate above them, heat and pressure gradually build. Over millions of years, these conditions may rise to a point where the crystals can no longer remain solid. They begin to melt, blending into the viscous embrace of liquid magma. In this molten state, the arrangement of atoms is fluid and dynamic, allowing for the possibility of new forms. Should the environment shift again, as it often does in the rhythmic dance of geological processes, this magma can cool and solidify, giving birth to new crystalline structures. Each new formation reflects the unique conditions that surrounded it, capturing the essence of time and change. The cycle continues, a gentle flow from solid to liquid and back again, illustrating the dynamic nature of the Earth's interior. Crystals that once shimmered in their intricate patterns may fade into liquid, only to rise again, transformed and shaped anew. This quiet journey of change within the Earth's depths invites wonder, an unending story etched into the very fabric of the planet itself. Beneath the surface, where temperatures rise and pressures build, crystals experience a subtle yet profound transformation. Over vast spans of time, existing crystals can alter their internal arrangement as heat and pressure cause them to dance silently at the atomic level. Atoms that once sat comfortably in one structure may move and shift, finding new positions in a different arrangement. For instance, the simple structure of graphite, often seen in everyday items, can metamorphose into the dazzling complexity of diamond under these intense conditions. This change is more than superficial. It involves a complete reordering of the crystal's internal framework. The once layered, flat planes of graphite, with their softness and ease of wear, become the strong, sparkling lattice of a diamond, renowned for its hardness and brilliance. Such transformations unfold quietly over millennia, a gentle reminder of the dynamic processes inherent in the Earth's crust. The crystals, in their various forms, are continually reshaped by the flowing currents of pressure and heat deep within, creating a mesmerizing cycle of change. Here, within this hidden realm, the world of crystals continues to evolve, resting in a state of serene transition. Within the heart of each crystal lies an intricate dance of atoms, where the alignment of electron spins creates internal magnetic forces. These forces are not merely fleeting, they can linger over extensive geological timescales, quietly influencing the behavior of the crystal. The arrangement of electrons within the atoms of the crystal determines the strength and direction of this magnetic property. As a crystal stands firm in its surroundings, external magnetic fields can gently interact with its internal structure. This interaction can induce shifts within the crystal, affecting how it responds to the environment over time. Even in the stillness of geological epochs, these internal magnetic forces remain stable, a testament to the enduring nature of the crystal's atomic arrangement. The pathways in which these magnetic forces influence the crystal can be subtle, weaving through the fabric of the material itself. Crystals, composed of meticulously arranged atoms, hold the ability to record information about their surroundings, absorbing and retaining traces of the magnetic fields they encounter. This quiet symphony of electron spins continues, creating a backdrop of stability and change, offering a delicate snapshot of the world around them. The presence of these magnetic forces deep within the crystal brings a sense of continuity to its existence, even as the world outside shifts and evolves. In the depths of the Earth, where molten rock begins to cool and solidify, crystals emerge in a slow, gentle process. As gravity exerts its constant influence, it can subtly shape these crystals over long stretches of time. This force encourages growth in one direction, leading to a slightly elongated appearance. Each crystal, in response, stretches and adjusts, finding its form amid the currents of the cooling magma. This elongation unfolds gradually as layers of molecules stack delicately, each one influenced by the gravitational pull surrounding it. The environment plays a vital role, As the molten rock comes to rest, the crystals that form within possess a unique signature of this interplay. Their shapes, often stemming from both atomic arrangement and the gentle tug of gravity, reflect a history of patience and endurance. Even as the Earth shifts and evolves, these elongated crystals continue to tell a quiet story of their formation, forever hinting at the forces that shape them. Their tranquil existence is a reminder of the delicate balance within the natural world, where even the smallest influences can lead to profound changes over time. The quiet growth of these crystals highlights the beauty of patience in nature, a seamless dance of elements guided by gravitational embrace. Within each crystal, a predictable pattern emerges, characterized by specific types of atoms or molecules. These constituent parts weave through the crystal's structure, establishing a harmonious arrangement that is both stable and consistent. This fixed presence is essential, as it ensures that the properties of the crystal remain unchanged over time. As the crystal develops, the chosen atoms or molecules join together, forming bonds that create a solid framework. This orderly organization allows the crystal to possess its unique characteristics, such as color, hardness, and luster. Each crystal holds the story of its elements, revealed through its form and structure. The uniform distribution of these atoms throughout the crystal contributes to its durability, allowing it to endure the passage of time. As surrounding conditions fluctuate, the core composition remains steadfast, unaffected by external changes. This continuity speaks to the silent resilience of the crystal, a testament to the stability inherent within its very nature. Crystals, with their consistent properties, invite tranquility, reminding us of the calm order that exists in the natural world. In many crystals, the arrangement of specific elements unfolds in a consistent and predictable manner. This orderly distribution allows for a steady internal gradient, where each element finds its rightful place within the structure. Over long periods, this predictable organization contributes significantly to the crystal's stable chemical makeup. As time progresses, the carefully arranged elements continue to bond seamlessly, reinforcing the overall structure. This internal gradient remains uniform, bringing a sense of harmony that defines the crystal's identity. Variations are minimal, ensuring that the character of the crystal persists even as it exists within different environments. The enduring nature of this distribution is a quiet reminder of the stability found in the world around us. Each facet of the crystal reflects this inner balance, creating an unchanging essence amidst the shifting external conditions. In this way, crystals stand as lasting examples of nature's ability to create order and beauty from simplicity, each one a tranquil testament to the long-term stability of its internal world. The refractive index of a crystal is a constant that describes how light bends as it journeys through the material. This property is intrinsically linked to the crystal's specific composition and detailed structure, creating a fixed value that remains stable over time. Each type of crystal has its own unique refractive index, determined by the arrangement and types of atoms within its lattice. While the refractive index is fundamentally stable, external conditions can introduce minor temporary changes. For instance, significant fluctuations in temperature or mechanical stress might cause slight shifts in how light travels through the crystal. However, these variations are generally brief and do not alter the core essence of the crystal's refractive properties. In peaceful moments, when light filters gently through a crystal, the refractive index serves to create serene displays of color and pattern. This stable interaction between light and crystal offers a quiet depiction of nature's laws, reflecting a harmony that persists across time, regardless of the outside world. Each pass of light through its structure reinforces the crystal's constancy, providing a tranquil reminder of stability in a fluid universe. The journey of sedimentary rocks unfolds over immense stretches of time, marked by a continuous cycle of formation and erosion. In the beginning, small particles from weathered rocks, minerals, and organic materials gradually gather in layers. These sediments settle in quiet places, like riverbeds or ocean floors, where they build up slowly, one layer atop another. As the weight of the layers increases, the sediments become compacted, pressed closely together, transforming them into solid rock through a process known as lithification. Once formed, these sedimentary rocks are not static. Over millions of years, they are subject to the gentle forces of nature. Rain, wind, and temperature changes work over time, wearing away the surfaces, breaking the rocks down into smaller pieces. This slow erosion reveals the rich history contained within the layers, releasing sediments that can once again settle, continuing the cycle anew. This enduring process emphasizes a tranquil rhythm in the world, where rocks are formed and reformed, each stage gathering stories of the Earth's past, a cycle that carries on silently, peacefully, and persistently, ready to begin anew. Light travels through different materials at varying speeds, and when it moves through certain crystals, it takes on a special behavior known as refraction. This bending of light occurs because the structure of the crystal affects how light waves interact with it. The angles of the crystal's facets carefully guide the light in such a way that it shifts direction, creating beautiful patterns and colors as the light emerges on the other side. Over the years, these crystals may undergo subtle transformations. When exposed to sunlight over long periods, the vibrant hues of some crystals can begin to fade. This gradual change is due to the energy carried by light, disrupting the delicate chemical bonds within the crystal. Each photon that strikes its surface can affect the arrangement of its atoms, slowly altering its appearance. This interaction between light and crystals creates a gentle dialogue over time, where both elements influence one another. The clear beauty of the crystals can be both persistent and transitory, reflecting nature's slow, quiet change. The process continues, a harmonious interplay that invites contemplation and stillness. Deep within the Earth's crust, immense pressure builds as tectonic plates shift and move. This pressure can have a profound effect on the crystals nestled within the rocky layers. Over long spans of time, the constant compression can cause these crystals to undergo a process known as recrystallization. As the forces continue, they gently reshape the crystals, bending them as if they were made of a very stiff liquid. This transformation allows new crystal structures to emerge, evolving from the original forms. With each passing moment, the arrangement of atoms within the crystals may change, creating unique patterns and forms. The once rigid structures become more pliable under the relentless embrace of the Earth's movements, revealing an elegant dance of geology that spans millions of years. The beauty of this slow process lies in its quiet continuity, a testament to the enduring power of pressure and time. Each crystal holds a record of its journey, fragile yet resilient, embodying the calm persistence of nature's transformative forces. In the depths of the Earth, hidden from view, crystals rest in tranquil geological formations. Here they endure for millions of years, shielded by the cool embrace of low temperatures and the weight of surrounding rocks. These calm conditions create a unique environment where the atomic lattice of the crystals remains unchanged, allowing them to exist in a state of remarkable stability. Surrounded by layers of earth, These minerals thrive in a world where time flows slowly. The cool temperatures play a crucial role in preserving their structure, preventing the atoms within from drifting apart or degrading. Each crystal takes on a character of its own, a quiet testament to the forces of nature that have shaped it over countless eons. The arrangement of atoms remains steadfast, forming solid bonds that give rise to the beautiful geometric forms we admire, all while enveloped in a serene stillness. In this underground sanctuary, existence flows along an unhurried path, a harmony of stability and time that lingers quietly, ready to reveal its secrets when the world above calls for new beginnings. Within the realm of crystalline structures, ferroelectric crystals exhibit a gentle yet intriguing property known as spontaneous electric polarization. In their natural state, these crystals possess an internal arrangement of charges that creates an electric field. This polarization is unique as it exists without any external influences. When an external electric field is introduced, the arrangement of charges within the crystal can shift, allowing this internal polarization to be reversed. This behavior is rooted in the delicate balance of forces at play within the crystal lattice. The orientation of ions adjusts according to the energy applied, leading to a transformation in their electric characteristics. As the field is removed, the crystal tends to return to its original state, holding on to its new configuration for as long as that state is stable. Such reversible changes occur with an elegant simplicity, revealing the inherent interplay of structure and energy within these materials. In the stillness of their formation, ferroelectric crystals continue to hold this remarkable potential, embodying a quiet complexity that invites exploration, waiting patiently in their peaceful state. Subtle changes in Earth's orbit and axial tilt weave a slow and intricate pattern known as Milankovitch cycles. These variations, unfolding over vast stretches of time, shape the distribution of solar radiation that reaches different parts of the planet. The tilt of Earth's axis, for instance, affects how sunlight is spread across latitudes, creating gentle shifts in climate. These changes can be gradual, occurring over tens to hundreds of thousands of years. The interplay of these cyclical movements influences the rhythms of ice ages and interglacial periods. As the tilt and orbit adjust, they modify the warmth of the sun's rays, nurturing periods of glacial advance or retreat. Each cycle intricately contributes to the long-term climate changes, hinting at a dance between the Earth and the cosmos. Within this continuous cycle, our planet experiences a careful balance, resting in its orbit while responding to the delicate pull of gravitational forces. The quiet unfolding of these cycles reveals the Earth's own natural timekeeper, patiently marking the passage of ages, holding within it the promise of change and continuity. In the structure of a crystal, there exists an essential characteristic known as the elastic limit. This threshold delineates the maximum amount of stress the crystal can withstand before it begins to undergo permanent deformation. As external forces act upon the crystal, it responds with flexibility to a certain extent, allowing it to return to its original shape once those forces are removed. However, when the applied stress surpasses this delicate boundary, the internal bonds within the crystal lattice can become permanently altered. The precise arrangement of atoms within the crystal contributes to its resilience, creating a stability that is both strong and fragile. When tension builds and exceeds the elastic limit, the once harmonious structure can reveal its vulnerabilities, resulting in changes that cannot be reversed. This process exemplifies the profound interplay between the forces of nature and the orderly architecture of crystals, Observing these transitions quietly emphasizes the intricate balance within the material world, showcasing how strength and alteration coexist. Each crystal carries within it the memory of stress and shape, ever poised in its crystalline beauty, yet affected by the gentle dance of pressure around it. Within certain crystalline structures, a fascinating phenomenon occurs, known as clathrate formation. In these unique frameworks, the crystalline arrangement creates porous cavities that can enclose gases or liquids. This property is a gentle reminder of the complexities that exist in natural formations. When conditions are just right, the host framework can stabilize these trapped substances, allowing them to remain in place for an extended period. The geometry of the crystal plays a significant role in this process. Depending on the specific arrangement of atoms, the size and shape of the cavities can vary, allowing different types of molecules to fit within the framework. These host-guest structures can exist harmoniously, each contributing to the stability of the other, like a quiet balance in a still pond. Under certain pressures and temperatures, these clathrates remain stable, holding the enclosed substances in a delicate embrace. This intricate dance of atoms and molecules illuminates the serene interplay between structure and stability, revealing a world where even at microscopic scales, order and complexity thrive in unison. In this ongoing existence, there lies a sense of calm, a soft reminder of nature's quiet creativity, ready to continue exploring the wonders all around. Certain crystals possess a remarkable property known as piezoelectricity. This means that when mechanical stress or vibrations are applied, they can generate an electric charge. This phenomenon occurs within the internal structure of the crystal, where the arrangement of atoms allows for a shift in electrical energy in response to external forces. When pressure is applied, the delicate balance of the crystal's atomic framework shifts ever so slightly, leading to the release of electric energy. This response, while often rapid, can take a toll over time, as constant mechanical stresses may lead to gradual wear on the crystal's surfaces. The tiny discharges that emerge from this process create subtle changes, almost like whispers through the structure, each small shift contributing to the wear of the material. The beauty of piezoelectric crystals lies in their inherent ability to transform mechanical energy into electrical energy, creating a gentle interplay between movement and charge. And as the crystal ages, the history of these tiny interactions becomes etched into its delicate surfaces, each imperceptible change telling a story of energy elegantly woven within its form. This ongoing process invites a tranquil energy, a harmonizing rhythm that quietly continues through time, ready to reveal more of its secrets. Crystals possess a fascinating feature known as polymorphism. This allows them to take on different internal structures while maintaining the same chemical composition. Over time, under specific conditions, such as changes in temperature or pressure, the arrangement of atoms within the crystal can shift gently, creating a new but equally stable structure. The internal framework of a crystal is not rigid, it is more like a delicate lattice that can adapt over long periods. This transformation can occur slowly, with each atom finding its new place in a different configuration. While all these forms share the same basic identity, they can exhibit distinct physical properties. These changes remind us of the dynamic nature of materials, even those that seem solid and unchanging. The different arrangements reveal how diverse the world of crystals can be as they gracefully transition from one form to another. The rich tapestry of their structures is a quiet reminder of continuity, stability, and the gentle flow of time, ever ready to embrace new possibilities. The cohesive forces that bind atoms in a crystal form a remarkably stable internal structure. These forces arise from interactions between atoms, drawing them together with significant strength. As a result, crystals exhibit a notable resistance to deformation, maintaining their integrity through various environmental changes. This stability is reflected in their high melting points, a testament to the immense binding energies at play. When heat is applied, the energy must overcome these strong cohesive forces for the crystal to reshape or change phase. The balance between the energies of the atoms creates a harmonious arrangement where each atom finds its specific place in an orderly, repeating pattern. The layers of atoms work together, forming a cohesive whole that is both resilient and beautifully structured. This deep stability allows crystals to endure in their form, withstanding a variety of conditions without losing their fundamental nature. As time flows gently by, the intricate atomic arrangements quietly hold the potential for transformation, demonstrating the remarkable nature of these captivating structures. The gentle rhythm of breath weaves through the quiet of the night. Thoughts begin to rest, settling softly within the mind. Each moment stretches, inviting a sense of calm. The world outside is wrapped in stillness, and within there is a tender peace. In this serene space, you can feel the warmth that surrounds you. It embraces the mind, easing any lingering tension. The silence invites comfort, wrapping you in its embrace as you merge into the soothing depths. Soft echoes of light and sound blend into a harmony that cradles the spirit. This tranquil stillness holds the promise of rest. Each gentle heartbeat slows, allowing the heart to find a steady, soothing pace. The gentle hum of tranquility lulls you deeper, filling the senses with warmth. As thoughts drift like clouds across a soft sky, they begin to fade gently away, leaving behind a deep sense of peace. The world feels safe as shadows embrace the calm. Here, everything is held softly, and you may find your eyelids growing heavy. Allow yourself to float on this serene current, surrendering to the stillness that surrounds you. Embrace the quiet of the night as you slip into the gentle embrace of sleep. Good night from Sleepy Science Facts.